In this video, we are going to consider the motion of a particle moving with constant speed around a horizontal circle. Now, in the previous video, we established that if a particle of mass m is moving in a circle of radius r meters with constant angular speed omega radians per second, then the speed of the particle is given by v equals r times omega and is tangential to the circle, and the acceleration of the particle has magnitude omega squared r, which is the same as v squared over r, where v is the speed, and the acceleration is always directed towards the centre of the circle. Now, Newton's second law therefore implies that the particle must have a resultant force of magnitude m omega squared r, or mv squared over r, directed towards the centre of the circle. This resultant force is called by the physicists the centripetal force. However, in our mathematics work, we tend to avoid the use of the term centripetal force. Instead, we emphasize the process of drawing a clear force diagram for the situation, clearly marking on the diagram an acceleration of magnitude omega squared r, or v squared over r, acting towards the centre of the circle, and then applying Newton's second law. Indeed, we'll find that the following strategy will solve almost all of the horizontal circular motion problems that you will encounter. Begin by drawing a very clear force diagram for the problem. Mark on an acceleration of magnitude omega squared r, or v squared over r, towards the centre of the circle. You may need to use some geometry or trigonometry to calculate any required angles or lengths. And then we will apply Newton's second law in two directions. First of all, we'll apply Newton's second law vertically, remembering that there is no acceleration vertically. And then secondly, we will apply Newton's second law towards the centre of the circle. Now, you'll see this strategy in use in all of the following examples. So let's have a look at our first example. We have an inextensible string of length 2.5 meters as fixed at one end A, and carries at the other end a particle of mass 0.4 kilograms, which is rotating with constant angular velocity in a horizontal circle whose centre is 1.5 meters vertically below A. We have to find the angular velocity of the particle and the tension in the string. The first thing we'll do is try and draw a diagram showing the situation, and here you can see that we've got our fixed point A, and we've got the particle is going in a circle around a point which is 1.5 meters below A, and it's held in that circle by a string of length 2.5 meters. We will certainly need to know what the radius of the circle is, and we'll also need an angle that the string is making with the vertical. So looking first of all at the radius, we can use Pythagoras' theorem. We've got 2.5 squared equals r squared plus 1.5 squared. So r is the square root of 2.5 squared minus 1.5 squared, which gives me 2 meters. The angle that the string is making with the vertical, we'll call the angle theta, and looking at the triangle again, we can see that the cos of theta is the adjacent over the hypotenuse, so that is 1.5 divided by 2.5, which is 3/5, and the sine of theta is r divided by 2.5, so that's 2 divided by 2.5, which is 4/5. Now we'll produce a second copy of the diagram, and at this stage we'll show that the particle is going round the circle with angular speed omega radians per second, and we will add the forces and the accelerations to the diagram. So the forces acting on the particle are its weight of 0.4 g and the tension in the string, which we shall call T. We know that the acceleration acting on the particle has size omega squared r and acts towards the centre of the circle. So we've got an acceleration of omega squared r towards the centre of the circle. So we're going to apply Newton's second law now, and first of all we will use Newton's second law vertically. So that gives me the vertical component of T, and by alternate angles we can see that the angle that T makes with the vertical is also theta, so we've got the vertical component of T is T cos theta minus 0.4 g gives me the resultant force, and that must equal the mass times the acceleration vertically, but there is no acceleration vertically since the particle is moving in a horizontal circle. So we've got T cos theta minus 0.4 g must equal m times naught, in other words, naught. So that gives me that 3/5 T minus 0.4 g equals naught. So 3/5 T must be 3.92 newtons. So T must be 6.53 newtons. And if we now apply Newton's second law towards the centre of the circle, then we've got the component of T towards the centre of the circle, or component of T to the left in our diagram, which is T sine theta, must equal m times omega squared r. So in this case, we've got T sine theta must equal 0.4 times by omega squared times by 2. We know the value of T, so we've got omega squared is T sine theta divided by 0.8, which is 6.53. So omega is the square root of 6.53, which is 2.56 radians per second. For our second example, we have two light inextensible strings, AB and BC, each of length A, are attached to a particle of mass m at the common point B. The other ends A and C are fixed to 2 points in the vertical line, such that A is distance little a above C. The particle describes a horizontal circle with constant angular velocity omega, with both strings taut. We've got to find the tension in each string and the minimum possible value of omega. So again, we must start with a diagram. So we've got our fixed points A and C, and then we've got the particle is at B, and the particle is rotating around the vertical line AC with constant angular velocity omega. Now, our first observation should be that we have got an equilateral triangle ABC, which certainly means that each of the three angles is 60 degrees. And if I just consider the triangle consisting of A, B, and the centre of the circle. Well, that's a right angled triangle, so I've got R divided by A is the opposite over the hypotenuse for the 60 degrees, so we've got R divided by A is equal to sine 60, so R must be A sine 60, so R must equal root 3 over 2 times A. We need a second diagram to put all of the forces and the acceleration on. So the forces that we've got acting on B consist of, first of all, the weight of B, so that's mg. And then we've got the tension in the string joining A to B, which we're going to call T. And we've also got a tension in the string joining B to C, and we'll call that S. In this case, they are two distinct strings. There's no reason at all why the tension in the two strings should be the same. So we must be careful not to assume they're the same. We must be careful to call them something different. So we've got T and S for the two tensions. Okay, and then we've got the acceleration towards the centre of the circle, which is of size omega squared r. So we're going to start resolving again. We know that the angle that the vertical makes with the string AB is 60 degrees, and therefore again by alternate angles we know that the angle that the force T makes with the vertical is 60 degrees, and the angle that the S makes with the vertical is 60 degrees. So applying Newton's second law vertically, first of all, we've got the resultant force, which is T cos 60 minus S cos 60 minus mg, must equal the mass times the acceleration vertically, but there is no acceleration vertically, so we've got T cos 60 minus S cos 60 minus mg must equal 0. So that gives me a half T minus a half S equals mg, because cos 60 is a half. Or in other words, we've got T minus S must equal 2mg. Now we're going to apply Newton's second law towards the centre of the circle. And in this case, we've got the component of T to the left, which is T sine 60, plus the component of S to the left, which is S sine 60, must equal the mass m times by omega squared r. Now we know that sine 60 is root 3 over 2, so we've got T times root 3 over 2 plus S times root 3 over 2 must equal m omega squared times by r, which is root 3 upon 2. So if we divide through by the root 3 upon 2's, we're ending up with T plus S must equal m omega squared a. So what we now have is we have a pair of simultaneous equations for T and for S. So if we add the two equations, we get 2T equals 2mg plus m omega squared a. And dividing by 2 gives us T equals mg plus a half m omega squared a. If we take the second equation and subtract the first equation, then we will eliminate the t's, and that will give us 2s equals m omega squared a minus 2mg, and dividing by 2 gives us s equals a half m omega squared A minus mg. Now the tension in the top string is definitely positive. However, the expression a half m omega squared A minus mg can be negative, and we can't possibly have a negative tension in the bottom string. So what we need to say is the minimum that the value of S must be greater than or equal to 0, because the string BC is taut. That means that a half m omega squared A minus mg must be greater than or equal to 0. In other words, a half m omega squared A has got to be bigger than mg, which means that omega squared must be bigger than 2g divided by A, so omega must be bigger than the square root of 2g over A. So the minimum possible value of omega is root 2g over A. Moving on to our third example, we have a string of length 25A has a smooth ring of mass m threaded onto it and is fixed to 2 points A and B, with AB equals 15A and A vertically above B. The ring is made to rotate about B in a horizontal circle. We've got to find the radius of the motion and find the tension in the string and the speed of the ring. Well, the first thing we must do is draw a diagram to illustrate the motion. So here is the particle, the ring, which we're labelling P, and we've got the string which is going from A to P to the point B, which is 15A vertically, 15 times little a vertically below big A. And the ring is moving in a circle around the point B. Now the first thing we need certainly to do is to find the radius of the motion. We know that the length of the string is 25A. So if the radius of the motion is r, then we've got r plus AP must equal 25A. In other words, AP is 25A minus r. Now we've got a right-angled triangle whose longest side is 25A minus r and whose two shorter sides are 15A and r. So, using Pythagoras' theorem on the triangle ABP, we can say that 25A minus r all squared is equal to 15A squared plus r squared. Expanding, we've got 625A squared minus 50AR plus r squared on the left-hand side equals r squared plus 225A squared. The r squareds clearly cancel, and we end up with 400A squared equals 50AR. And dividing by 50A, we end up with r must be 8A. Now at this stage then we'll update our diagram. So we now know that the radius is 8A and that the hypotenuse is 17A. And we can now get some information about one of the angles. So again we'll do the angle between the string AP and the vertical. I'll call that theta. So we've got cos theta is the adjacent over the hypotenuse, which is 15 over 17, and sine theta is the opposite over the hypotenuse, which is 8 over 17. Now to find the tension in the string and the speed of the ring, we're going to need to have a nice clear force diagram which shows the acceleration of P as well. And we're going to need to use Newton's second law again, both vertically and towards the centre of the circle. So to add the forces, first of all, we've got the weight of the ring, so that's mg vertically downwards. We've then got the tension in the string AP acting on the ring, and we've also got the tension in the string BP acting on the ring. Now in this case, because we have got a single string A, P, B, and that the ring P is nice and smooth, the tension in the string is going to be the same in A to P as it is in B to P. So we've got the tension T acting in the string AP, and we've also got the tension T acting in the string element BP. So, finally on our diagram, we need to put the acceleration on. Looking at the question, in this case the question is asking us for the speed of the ring, not the angular velocity of the ring. So we'll put the acceleration in the format v squared over r in this case, rather than putting the acceleration as omega squared r. So, taking Newton's second law now and applying Newton's second law vertically, we have got the vertical component of t. Now that's the t in the element AP of the string, is t cos theta, minus mg, and the component of t in the element BP of the string in the vertical direction is 0, so we don't need to take any account of that at all. So the resultant vertical force acting on the string is t cos theta minus mg, and that equals the mass times the acceleration vertically, but the acceleration is horizontal only, which means there's no acceleration vertically, so our Newton's second law equation vertically is t cos theta minus mg equals 0. So that's 15/17 t, take away mg equals 0, 15/17 t equals mg, so t is 17/15 of mg. If we apply Newton's second law towards the centre of the circle, then we've got a component of t sine theta to the left from the element AP of the string, plus t is the resultant force, and that must equal m times v squared over r. So we've got 17/15 mg times by 8/17 plus 17/15 mg equals mv squared over 8a. This simplifies to 5/3 mg equals mv squared over 8a. So the m's cancel, and we get v squared equals 40 ag divided by 3. In other words, the speed of the ring is going to be the square root of 40 ag divided by 3. And that finishes our video on motion in a horizontal circle with constant speed.